I'm sorry, I haven't posted the recording from yesterday yet because frankly, I don't know where Zoom actually stores the recording, but I'll find that and post it. And I'll do it again for today. So today I want to cover something, I guess, new. And I'll explain my reasoning behind that. So today we're going to do something called kinematics. And the reason I'm happy to do it today is because Miss Crawley and I have talked, and it's not going to be in the upcoming SAT. We normally would put it in the SAT, but we've just made an agreement, given everything that's going on, that we won't put kinematics in the SAT. However, we don't have that agreement with the SACE examiners. Kinematics is still in the course. So even though we're not going to put it in the SAT, and frankly, his class doesn't have time to cover it, we do have time, that is, and I think we're going to have to cover it at some point anyway. They're going to have to do it probably during the end of term 3, start of term 4, right before the exam weeks. There's not really a good time to sneak in kinematics. It sensibly fits here. So we're going to do it here, and I'd like to have a shot at it and a bit of practice today so you get a little more comfy with it. But just bear in mind that it's not in the upcoming SAT.
Does that mean it will be in the exam still though?
Yeah, well, yeah, it will be in the exam, so we have to cover it eventually. And I think might as well do it now. Yeah, and we don't write the exam, so yeah, it could easily be in the exam, but we're just giving you a heads up, is not on the SAT. So you guys get notebooks out. Have fun with this, Ivan.
Oh, give me a second.
And your title is, to start with, kinematics. Type it in. And your first little subtitle is displacement. And for those of you guys who have done or are doing physics, I'm hopeful that you'll have a pretty comfortable idea of the difference between distance and displacement, and speed and velocity. But I will go through it again just, in case. All right. So distance in math is how far away something is from something else. And displacement is very similar. But displacement is how far away we are from the origin. So displacement, let's say if we had displacement of -3, that would imply that we are 3 to the left of the origin. Or if we had a displacement as +7, we would be 7 to the right of the origin. So note that if it was a displacement of -3, it might be 3 away from us in terms of distance, but the displacement has that sign as well. So displacement is just a fancy word for distance, and it will generally have a plus or a minus sign, which we interpret to be the left or the right of the origin. In Year 12 maths, we only really consider objects moving in a straight line. So we'll only consider particularly particles moving left and right. Left being negative, right being positive. And don't ask me why we do this, we define displacement as S of t. And S is the physics letter they use for displacement. And we say it's a function of time. So displacement changes over time. And what you're likely to see is some sort of graph looking like this. So you don't have to copy this graph down, but I just like to sort of talk you through it because you will have seen these types of graphs before. This is the story of a particle moving to the right because entire graph displacement graph is positive, so it's going completely to the right. Initially, it moves away at an increasing speed. That curve indicates it's accelerating away. Then it reaches a speed it's happy with, and that straight line means it's moving away, but at a constant rate. So it's reached a certain speed, it's not accelerating or decelerating, it's not getting faster or slower, it's just moving away at a constant speed. There's a third little portion here that indicates it's slowing down. It's still moving away, but it's slowing down. And then at horizontal, it'll be at rest, so it's stationary. So time is still going by, this axis can still go, but the distance is not changing. Have you guys seen this type of graph before? This displacement over time? It would have been like
Yeah, in physics.
leaving school or in physics. Yeah. All right. So the really neat thing is from this graph, we can actually calculate velocity and acceleration. And that's what today is about how to use a displacement graph to calculate velocity and acceleration and the relationship between them. So I guess your next little title will be velocity. Velocity is given by the graph VT, velocity over time. And you might remember velocity, or from year 10, you might remember that speed equals distance over time. In year 12, we update that a little. Instead of speed, we say velocity. So velocity has a positive or negative, depending which way we're going. And displacement instead of distance. But basically, the change is the same. Velocity is how far something's traveled, change of displacement over change in time. Now, hopefully you're looking at that thinking, change in displacement over change of time looks very much calculus-y, and it does. What we're saying is really, if displacement is on the y-axis, and it is, change in y over time on the x-axis, change in x, which leads to the very neat result that the velocity of an object is the first derivative of its displacement graph. So if you have an object with a displacement graph like the one we just looked at, and you find its slope at one point, its slope is how fast it's traveling. I'll just scroll up to look at this graph again. If you imagine its slope at this point here, it's positive. That means it's moving to the right, and it's not traveling very fast. But at this point here, the slope increases. It's more positive now, so its velocity is faster. At this point here, it's slowing down, its velocity is lower. And finally, at this point in purple, the velocity is 0. The slope is flat. So as the curve changes, we can say that the slope of that curve, or the displacement curve, is the velocity, which is pretty cool. We can go one step further. You might notice how I mentioned that the acceleration or the speed was increasing. So here, for example, you see this portion of the curve that I'm highlighting in yellow now. That is when the speed is increasing. So the velocity keeps going up. When the velocity keeps going up, our original graph, if you take its second derivative, is greater than 0. It's concave up. Similarly, here, when the velocity is decreasing, it's concave down, s double dash t in that portion is less than 0. Simply put, the acceleration of a particle is the second derivative of its displacement function. So, AT is equal to the first derivative of the velocity function or second derivative of the displacement function. Am I going crazy fast for people trying to take notes?
Yeah, it's a bit too fast.
Yeah, I'm sorry.
It's all good. Oh, we're not doing physics lesson, right?
No. It feels like it though, doesn't it?
I'm not doing physics anyway.
Do you reckon you could just go back up to the velocity thing? I just
After
got
the-
the
after
last little bit to
displacement.
copy.
Is
Thank
this bit?
you. Yeah, like 2 more seconds.
We don't need to. We don't have to like remember what velocity is. Like, we don't have to remember to describe what velocity is, right?
Wait, for physics?
No, I mean in math.
No, for maths, you just need to know that velocity is the first derivative of the displacement function.
And can you show the graph in that you have shown in when you're talking about the displacement?
Oh,
Oh, just acceleration, constant accelerating decrease, and stationary. The gradient degree. Okay.
now I do have more notes that we'll come back to, but I think at this point it might just help if we go to an example, because these questions are pretty predictable in what they ask. So if you've got the textbook with you, I'm basically going to talk us through the example from page 80. And page 80 looks like this. A particle moves in a straight line with position relative to O given by st equals t cubed minus 6t squared plus 9t, take 1, where time is in seconds and t is greater than or equal to 0. A really good thing, a way to start this is to graph it. So I'm just going to graph this function. And you guys will be able to see what's happening to the particle. Minus 6t squared, 6x squared. Yeah, your calculator won't understand t, so don't put t in there. Put in x. 9x minus 1. All right, so what this particle is doing, it is starting somewhere here. As it goes up, the particle is moving to the right. Then it stops, moves back towards the origin, passes the origin, goes to the left of the origin, stops, turns around, goes right, away, and just keeps going off into the distance. That curve is a story of where the particle is in relation to the origin. You can almost think of the origin as the x-axis. And if you turn the x-axis like 90 degrees clockwise, it starts to the left, then moves to the right, then backwards. And that's like the story of how it goes. That probably, we'll come back to this graph in a second. In fact, I'm going to capture it and put it here. All right, part A, find expressions for the particle's velocity and acceleration and draw sign diagrams for each of them. All right, so its velocity, vt, is equal to the first derivative of ft. And because they start off with a nice polynomial, the first derivative is 3t squared minus 12t plus 9. And then we want a sign diagram for this. Any idea how you'd get key points on this?
You need to find the stationary point first.
Yes, you need to set this equal to 0 is 3t squared minus 12t plus 9.
Factorize the 3 out.
Yeah, good. Factorizing 3 out is an excellent start. 0 equals 3 bracket t squared, take 4t plus 3 If you didn't spot factorizing 3, that's okay. You could easily just put it into the quadratic formula from there. But this way will be quicker. 0 equals 3. Then we're thinking sum of product. What adds to -4 multiplies to +3 is x take 1, x take 3. Yeah, hoping we're happy with that.
T
Which
take
means
1, T.
our solutions are 1 and 3. 1, 3. So now we do a sign diagram. I would substitute in 0, the velocity function. If we sub in 0, it's going to be +9. If we sub in 2, what's that? 3 lots of 4 minus 12 lots of 4 plus 9. 12 minus 48 plus 9. Well, it's going to be negative, isn't it? That minus 48 is just dragging everything down negative. And then if we sub in the number 4, 3 lots of 16 minus 12 lots of 4 plus 9. 3 16s.
We actually don't need a test like this because we have already got a graph. We know which one is the local max and which one is the minimum.
Yeah, so true. We already have a graph. We can see it here, the minimum and maximum. So what this is saying is that the particle's velocity is positive between, well, 0 and 1. And what that is relating to this bit here. You see how the slope is positive there, meaning the particle is moving to the right. Then between 1 and 3, the slope is negative, meaning it's moving to the left. And then after that, the slope goes positive again. So it's essentially what we've done before in terms of creating a sign diagram, finding a max and min. But in this case, the positive and negative means its velocity is going one direction or the other. And note, a change in velocity is equal to a change in direction. When we go from positive to negative in velocity, there's a change in direction. But that's not necessarily true with acceleration. So we'll do the acceleration one as well. That's VT. AT is equal to the second derivative of t. And because it's a polynomial, it's pretty good. The second derivative is 6t take 12. And if we're going to do a sign diagram, we set it equal to 0. 0 equals 6t take 12.
For sure.
Solve for t, 6t equals 2. So our sign diagram, and this is for time of t. We can sub in a value less than 2, say 1, and it's going to be negative. And we sub in a value greater than 2, it's going to be positive. What that means is that the acceleration here is negative. ACC is negative. It means the acceleration is negative, meaning the particle is, you can think of it as slowing down or increasing its velocity towards the right, towards the left. On the graph, I might just bring it up, bring that down here. That negative portion is this bit here until we hit 2. Basically, the gradient starts off very positive, like 10, 5, 0, -1, -5. You see how through that entire portion, the velocity is decreasing. It's going from a very high velocity of 10 at the start, and then it decreases until it reaches like a -5 portion here at a guesstimate. What that means is that the entire process, it's decelerating. And some people get tripped up with here. The fact it's decelerating doesn't necessarily mean it's getting slower. It's decelerating, but in reality, it went from here, where it was stationary, here where it was moving, but going to the left. So decelerating does not mean slowing down. Decelerating means the particle is moving with increasing velocity towards the left. So if it starts off fast to the right, as long as it goes more and more left, which is that way, yeah, left, then what's happening is the particle is decelerating. And then it reaches here, and the slope starts getting less negative, 0, and then more positive, and that's accelerating. And note that accelerating doesn't always mean getting faster, because here it accelerates to the point where it actually stops and then keeps going towards more positive.
Oh, so like in the stationary point, I mean the turning point. So imagine this pencil is going to the right, and then it suddenly stops at that point that the velocity is 0. And
But
then,
acceleration is not 0. Yeah.
I mean, the velocity is 0.
Yes.
And then you move to the opposite direction,
Yeah.
but it still have the velocity, but it's decelerating.
Yeah. So another way to think about it, especially for those who have done or are more comfortable with the science, is the acceleration due to gravity is pretty constant. If I take my little rubber ducky, and throw it up in the air, there will be a point in the air where it stops moving. It will fly up to a point, stop, and come down. So it moves fast when I throw it, it slows, it stops, and it drops. So its velocity, if I'm saying up is positive, its velocity will be positive, 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 0, negative. However, for the entire time, the acceleration is negative because the positive velocity is getting smaller, it hits 0 and then goes negative again. So the acceleration due to gravity is always negative, but it doesn't mean the velocity is always negative. All right, anyway, that's the 2 sign diagrams for part A of the question. What is it? Find the initial conditions and hence describe the motion at this instant. The initial conditions basically want you to find S0, S0, V0, and A0. They want you to find its displacement, velocity, and acceleration at time equals to 0. So S of 0 is -1. If you imagine putting in 0 to that, you're just going to get the constant at the end, it's -1. And you can see that on the graph, it's down here. V of 0, if you shove 0 in there, it is 9 meters per second. And acceleration, if we shove in 0, is -12 meters per second squared. So describe the motion at this instant. The particle starts 1 meter to the left of the origin. It starts moving 9 meters per second to the right, and it's accelerating 12 meters per second squared to the left. So the initial conditions are how it starts off. So it starts off to the left of the origin. Wait, it's reversed for you guys, isn't it? To the left of the origin, moving this way, but the acceleration is slowing it down.
Can you like explain that again?
Yeah,
That
right.
Let's just explain again next week.
We're doing this today because next week we'll want to revise for the SAT.
Oh,
Yeah.
savage.
All right, so we've got Ducky. If here's the origin of my hand, and that's right for you guys, isn't it?
Yeah.
Yeah, cool. Ducky starts 1 meter to the left of the origin. And when he starts moving, he's moving at a speed of 9 meters per second this way. His acceleration though is negative. The acceleration is going back that way. What that means is that as soon as he starts moving, in the first second, he would have gone 9 meters because that's 9 meters per second. But his next second will be less because his speed is going to be less because his acceleration is going
Oh.
back that way. So his
So like
initial,
slowing down.
yeah, yeah, slowing
yeah.
down. So it's like, frankly, this ducky right now is a bit like me at the
Yeah.
finish line of a race. I haven't reached it yet. I'm tired, so I'm moving this way, but I'm slowing down to get there.
Okay. You're like, imagine like there's like something to push it over, so like it's slowing down.
Yeah, so
Something.
you can still be moving forward but slowing down. It's a bit like if you're driving your car and you hit Upper Sturt Road, you're moving forward, but then as you hit the hill, you start slowing down a little. You're
Very
still
confusing.
you're still going forward, but you're slowing down.
So what's with the -12?
-12 is its acceleration. So it's the acceleration at time equals to 0. It's if you sub t equals 0 into the second derivative. And if 6 zeros is nothing, so -12, it means that a of 0 is -12. It means that the acceleration is pulling him to the left. That way. All right, I'll jump on to C. Find the position of the particle when it changes direction. Does anyone happen to have a shot at this?
Like I think it's turning point.
Yeah, exactly right.
Equals to 0.
Yeah, so when S of t equals to this happens when S dash t equals 0. And on the graph, it happens there and there. So it changes direction at 1 and 3. Draw a motion diagram for the particle. All right. To be honest, I've never seen this asked in an exam, but I'll show you what a motion particle looks like. Yeah. Basically, a motion particle is, here's the origin. What happens is the particle starts 1 meter to the left. It then travels to the right until it's 3 meters high. So I'm reading that off the graph. It looks 3 high there. I could p-solve. Is that 3 or 4? 1, 2, 3. I could p-solve and find that out. And then a motion diagram is literally this.
Wait, but doesn't it go left first?
Right first. If here's the origin, it starts to the left and then goes right. Wait,
So you start at left.
is my OneNote reversed for you guys as well?
No.
Is that way right?
Yeah.
Yeah, that's right.
Yeah. Yeah, that's right.
Right. Basically, on the graph, when it's going up, when it's increasing, like this portion here, the particle is moving to the right. So the journey of the particle starts here and goes this way, which on a motion diagram is starting at -1 and going this way, and then it will curve back round to -1, and then curve back round and go off that way. And that final bit is this final bit here. And if you look at the answers, it's truly bizarre. It is literally a little picture of a particle doing this wibble wobble.
So is it because it's like tilting right, not actually like it's going? Because I thought it was like it was going like left into like the positive of the. Is it because it's actually tilting that way, or like because I was looking at it like you flip it, and then it actually goes like left. Is it just the way like it's tilting?
Oh, I see what you're doing. Hang on, I'll see if I can rotate it.
So Mr. Bunderberg. So like when
Yeah, it kind of
Right.
works like this.
Eh.
When the particle is above the x-axis, it's to the right of the origin. So it goes right, left, right.
Yeah, like I flipped it the other way, so it was like that's
okay.
why I got confused.
Yeah, sorry. Yeah, definitely flip this way. Or I probably wouldn't, maybe flipping is a bad idea. It's remembering that when it's positive, it's to the right. And when it's negative, it's to the left.
So you start at -1 and you move to 3, and on the way to 3 it starts slowing down, and then
Yeah,
at 3 the velocity is 0,
yeah,
and
good.
it goes backward. I mean the left, and on the way and it slow down again. So
Yeah.
that's why the acceleration is negative, and then at the turning point it just go back to the right again.
Yeah, nice.
Ah.
So is it just drawing like the value of y?
Yeah, pretty much. You're drawing the value of y, but imagining it on a flat plane, going left and right instead of y and being positive and y being negative.
Oh, okay.
Wow.
What time interval is the particle speed increasing? All right. Speed. I've got to clear some space here. Do you mind if I delete all that stuff? Speed is increasing when AT
Accelerating.
is greater than 0. Yeah, so when AT is positive, speed is increasing. When AT is negative, speed is decreasing. And if we're looking for when AT is positive, we can look at the sign diagram for AT and see that it is between 2 and to infinity. So I would say the answer for this is when t is greater than 2. All right, find the total distance traveled in the first 3 seconds. The total distance traveled is a good use of the motion diagram, and this sounds ridiculous, but in the first 3 seconds, hang on, let me just check what the first 3 seconds is. Draw, desolve, y count 3. All right, first 3 seconds is we get to here, yeah? The total distance traveled is we go from -1 up to 3. That's distance traveled 4 so far. Then we go from 3 high back down to -1. So we're traveling another 4. So the total distance we travel in the first 3 seconds is 8.
How would you express that in units? Is it just like 8 grid boxes or?
I think we assume just meters. Hang on, there might be something in the question for it. Oh no, here. Centimeters. Which means my velocity should have been centimeters per second and my acceleration should have been centimeters per second squared. But yeah,
If you do that in a SAT and the SACE exam marking, would you lose marks?
probably not. They're not as finicky as they are with science in terms of units. But I mean, try to get it right. It's better that way. But no, you'll be fine. So total distance traveled 8 centimeters. Note, there is a trap type question here. If they asked, what is the change in displacement after 3 seconds? Can anyone tell me what the change in displacement is after 3 seconds?
-1.
That, I guess the displacement at 3 seconds is -1. The change in displacement, and this is brutal, is 0. Because at time equals 0, you started at -1. So the change by the time you get 3 seconds in, you haven't changed, you're still at the same point of -1. So when it says change in displacement between, say, 0 and 3 seconds, you're looking at how far that's changed in the 3 seconds.
If you have s of t and you put s of 3, what will you get? Because that's the displacement of 3 seconds, I thought.
Yeah, but sorry, my keyword is the change in. Because you're right, you will get -1, but I could probably word this better, between 0 and 3 seconds. If we're looking at change in displacement between 0 and 3 seconds, we haven't changed our displacement at all. We've certainly moved distance, but the displacement hasn't changed. All right, I probably confused people. Would you like me to grab another practice question? We go through something similar?
Yes, please.
Sounds good. Let's grab. More tricky one.
How many sheep are in a herd?
Don't know. All right, so we're going to do 3EQ7. But if there were 7 sheep in a herd, you could just say 10 because you rounded them up. All right. Anyway, awesome place to start with these is graph them. An object has a displacement function st of t minus ln 2t plus 1, where t is in seconds. And note that we're talking centimeters here. Show that the object is initially at the origin. All right, so the initial placement of the object is s of 0. And we put in 0 minus ln 2 lots of 0 plus 1. All right, this is minus ln of 1. The natural log of 1 is 0. So that would show that when time equals 0, the displacement is 0. So we're starting at the origin. Find the velocity function. All right, the velocity function, vt, is equal, just vt, is equal to s dash t. So if we were going to differentiate this, it would be 1 minus, what is it, 2 over 2t plus 1. Yeah. All right. Over what interval of time is the object moving to the right or moving to the left? So when it's moving to the right, vt is positive. When it's moving to the left, vt is negative. What this is leading us towards is to draw a sign diagram for vt, work out when it's positive, when it's negative. So let's work that out. 0 equals 1, take 2 on 2t plus 1. Minus 1 equals minus 2 on 2t plus 1. Minus 2t minus 1 equals minus 2. Are you happy that I've multiplied that bottom up to here? There are negatives everywhere. If there are negatives everywhere, you can just multiply by minus 1. Get rid of them all. So therefore, 2t plus 1 equals 2. 2t equals 1 equals a half. So there's only really one point where this is equal to 0, and that's t equals a half. So our sign diagram for the velocity is going around a half. Note that, strictly speaking, you shouldn't end with an arrow here. That should just be a solid cutoff at 0, because time doesn't go on into the negatives. It should just stop at 0. All right, so we need to put in values either side of a half. I would put in a value of a 0. 2 over, well, 1 take 2 over 1 is, that's going to be negative. And then this side will be positive. So our interval when it's moving to the right is when, to the right is when t is greater than 0. And it's moving to the left when t is greater than 0, or greater than, what am I talking about? Greater than 2. not 2. A half. Sorry, everybody. So when it's negative, it's going to the left, positive going to the right. Show the object's acceleration is positive for all of t. Does anyone have a good idea how to do that?
Second derivative. That's
Yeah.
everything you need.
Excellent. So acceleration is second derivative. So let's find the second derivative. I'm going to do it over here. S double dash t. Well, if we take this, 1 derives off to 0. I'm going to write that as initially minus 2t plus 1, so the neg 1. That then differentiates to positive 2t plus 1 to the minus 2 multiplied by 2 from the inner derivative coming out, which can then be written as 4 over 2t plus 1 squared.
Square. Oh, yeah.
Yeah, because that was my minus 2 there.
All good, all good.
All right. If we look at this, are we happy that this is always greater than 0? And the
Yeah.
reason we should be happy it's always greater than 0 is because this
Because
bit
t
here,
cannot be 0.
yeah, t cannot be negative, and t cannot be 0. But no, t can be 0, but t can't be negative. Even if it was negative, it gets squared. Anything squared is positive, so it's really positive 4 divided by a positive number. It's always going to be greater than 0. So therefore, our acceleration is always greater than 0. And
Okay. So like
finally,
even though the velocity is negative, but like it's still speeding up.
yeah. Still, so what this is saying is the entire graph should be concave up. And we'll graph it on a calculator to double check the entire thing is concave up. Find the distance traveled by the object in the first 2 seconds. All right, let's grab a calculator and it can help us out.
Yeah, I think I understand.
Awesome. X minus ln 2x plus 1. And that's kind of what we
Nike.
predicted.
It's a Nike.
Yeah, it's like the Nike too. That's a pretty cool one, actually. It's an excellent function. All right. So find the distance traveled by the object in the first 2 seconds. If I was going to use technology to solve this, I would, first of all, just limit my x to 2. So I'm really only interested in what happens in the first 2 seconds. So between 0 and 2. So what I would do then is G solve minimum. That is not the minimum. That's the minimum. What's happening here is I drop down to minus 1.931 below the axis. And this occurs at x equals a half, which is what we saw from the turning point down here. So we go to the left, 1.93. Then we go back up to the origin. So G solve root there and here. You see how that down 1.93 and up 1.93 has happened twice. And then we want to know what happens at the end of the 2 seconds. So I would do ycal x equals 2.39. So if I was doing this as a sort of exam question, I'd be adding those 3 distances. I'd be adding that one twice. So 0.9315, 0.19, what is it? Wow, my memory is bad. 19315, and that twice. The reason I'm doing it twice is because I know that my particle has dropped that far away to the left, then back up towards the origin, and then is kept traveling to G-solve almost 0.4 to the right, so 0.93 to the right. .39 to the right. That would be the total distance traveled. Using the calculator, you could do it algebraically. You could do it algebraically by recognizing that you have a turning point at a half. So you sub in a half into the original function, and you would get a half minus ln, well, 2 lots of half is 1 plus 1, which is a half minus ln 2. And my bet is when you type a half minus ln 2 into the calculator, you're going to get this number here. You go down to a half minus ln 2, then it turns, comes back up, and then goes back up again for the second half of the 2 seconds. All right. I feel like I'm either confusing people more or less. Do you want to get into practice questions? Do you want me to show you the other notes things I had above?
Right, I don't understand how do you find the distance.
Yeah.
Okay, share again.
Yeah, I'm just going to give myself some space. All right, so distance is how far we move away from the x-axis. So what's happening with the particle is it starts at the origin. It moves left. So I was drawing its story. It would start at the origin, move left to a certain point, then move back to the right. So its journey is this. Now it hits here at time equals a half. And we showed that with the sign diagram, the first derivative, or we do G-solve minimum. It turns at time equals a half. So this happens at time equals a half, but the distance it travels is a half minus ln 2. And I get that by putting a half in where t is. Yeah? So when it moves, yeah,
so the distance from 0 moved to the left to the turning point is half take ln 2.
Yeah.
Okay.
And in a decimal, that's 0.193. But we can do it exactly. It covers that distance once, and then it does it twice to get back to the origin.
So we times it 2.
Yeah. So 2 lots of that.
Yep.
Then we want this. And this portion happens for the remainder of the 2 seconds. So this endpoint here will be the point given by s of 2. So when we put 2 into the displacement graph, it tells us where it is after 2 seconds. So we put in s of 2, which is 2 minus ln 5.
But that's just displacement.
Yeah, that's its displacement, which means, and that was what, about 0.39. But this point here is 2 take ln 5. So the particle's journey is to the left, a half take ln 2, to the right, another half take ln 2, and then continuing to the right until it reaches, well, 2 seconds in, at which point it is 2 take ln 5 away. So its total distance is the addition of those 3 sort of values there. Total distance traveled.
I hope I'll get it.
And it might come with a little bit of practice, or will be
Add them
practice.
together.
Pardon?
Maybe add them together.
Yes, you add them all together. So your answer would be 2 a half take ln 2 plus 2 take ln 5, which would give you, it would be a nasty decimal, but that's the end. That would be the calculator adding it together.
Can you just G solve for the first 2 seconds?
What do you mean?
Like plug in the graph, click G solve, type in
Yeah,
y x is equal to 2.
there.
Yeah, and then count the units.
But here's the trap though. That's the total displacement from him there. Like it's 0.39. You're right, that point is 0.39 high. The problem is that's not how far the particles traveled in total.
We're not because we're not calculating the straight line. We're calculating the curve, the length of the curve.
Well, not quite the length of the curve. We're calculating how far the particle's gone from the origin, or how far
Okay,
it's
so
gone.
you find the tangent that intercepts the origin and then find the length of that.
No, not the tangent.
Could you not? Like a chord from 0, 0 to there, like a direct line.
No, because that wouldn't be the distance it's traveled. It's like me saying, all right, can you picture yourself standing at the spectator area in the St. John's tennis courts, like looking towards the tennis court?
No.
Yeah, you can. You've stood there before. House tennis. You're looking at the tennis.
Okay.
Yeah. If I told you to go get a drink and then go to the other side of the tennis court, and then I asked you the total distance you traveled, the total distance you traveled is not the length of those tennis courts. The total distance you traveled is back to get a drink, forward to your initial spot, then forward again to the other side of the tennis court. So even though you've only changed your total displacement, you've only changed your spot by the length of the courts, the distance you've traveled is more than that change in location.
Right.
If you did a y-cal here and you say it's moved 0.39, you're ignoring the fact it's actually gone backwards, then forwards. So you're not calculating its total distance traveled, you're calculating how much it's changed by.
Right. Could you then, I'm just trying to think of like, so would that be the easiest way with the sign diagram, just adding the 2 values?
Frankly, I think the easiest way is on the computer. I would do G-solve minimum, and I would recognize it's done that distance twice. It's gone down to that, up to that, back to the origin. So I would double that decimal there.
Right.
And then I would do what you suggested, G-solve y-cal 2, and I would add that value on, because that way it's gone down that much, up that much, add on that.
Okay. So it's just using technology to find distance.
Yeah, but recognizing it can be done algebraically as well.
And in a question like scenario, I know we're not getting tested on it in this SAT.
Yeah.
Would they say like prove algebraically the distance traveled is, or like show that the distance traveled is this?
They could say show the distance traveled is this. They could also ask it in the non-calculator portion of the exam.
Damn, say so evil.
Yeah, they are, aren't they? They are. Anyway, so is there anything up here I was worth showing you guys?
Or some chuck a log multiplication into the non-calculator exam and me get 0 marks.
Yeah. All right. What I'd like you guys to have a shot at today is we've actually done number 7, so except 7. Have a shot at some of these questions. The first couple, like question 1 and question 2, I think are polynomial questions. They are very similar to that first example we did, and that's the example in the book. But have a go at these. The reason I'm keen to do it now is because next week we'll get more into SAT revision, and then of course our SAT is Thursday week 10. But I would like to just knock off kinematics, have some good notes and an idea of it until then. And there is a question or two, I think, in those exam booklets I've given you on kinematics as well that probably, hopefully, will make more sense after you've done some practice here.
So this second SAT,
Yeah,
is everything from the first sat, and then local max and min increasing and decreasing functions, stationary points in the second derivative, surge functions, logistics functions, and then not kinematics.
yeah.
Okay.
Yeah. And the reason I say everything from the first sat is simply because
Quotient.
the first sat was about being able to differentiate a whole number of different functions. And now we'll still ask you about those different functions, but this time we'll be asking you things like turning point and second derivative, etc. Yeah. So this sat probably feels bigger because it requires the knowledge from the from the first sat.
Mr. Bindenberg,
Yeah.
can I share my screen?
Yeah. Let me change security.
Wait a second.
Yeah, I've changed the security. It should let you share screen. Are we trusting you to do it?
Wait a second. Hold
Well,
on.
Ivan, don't disappoint. He's giving you the opportunity here.
Are we allowed to leave the call?
To do 3E?
Yeah.
Yeah, go for it.
All right, cool. Bye.
Hold on. Which one is it?
Bye.
I've got my cursor over something ready to put Ivan in a waiting room.
Can you guys see it?
Bring him in a waiting room. Where is he? More. Bye, Ivan. It could have been worse. All right.
He had one. He had one chance and he failed.
Oh, he left the waiting room. He bailed altogether. All right.
Bye.
It's because he forgot to share the sound as well. Rookie error. All right. Feel free to hang around if you have questions. Otherwise, have a shot at 3E, please. Oh, I see. Security. Don't just
He didn't get me.
need my food.
I have another question as well. A
Can I
legitimate
just answer?
math que-
Can I answer
A
one of
legitimate-
Phoebe's questions?
Pardon?
Can I answer one of Phoebe's questions?
Yeah, yeah,
I know
yeah.
Phoebe had a question.
Just yell at me and I'll come back.
Mhm. Hi, Phoebe.
Shout out to me there. Can we finish off 12?
Yeah. Let me just share my screen again. So we did D and we found the derivative.
Yeah.
And the derivative was this thing here.
Yeah.
All right. And then E asks the rate at which the population is increasing after 6 months. So the rate of increase is the first derivative. So it's the slope of the line, that's how fast it's changing.
Yeah.
And after 6 months, what it's telling you to do is put the number 6 into this equation. So just let C equal 6 into the first derivative.
Yeah.
It'll be a number. And that will be the rate of increase. So let's just pretend the number's 20. What that means.
I think that one will be fine. It's just because I didn't know what D was. I didn't obviously do that. So then I was like, well, it's kind of hard to substitute a number that you don't know in.
Yeah, fair.
So
Yeah.
that one will be fine. And sketch or graph will be fine.
Yep.
And then so that whole question's fine now. And then I didn't know how to do 13 of 3D.1 where you're like proving
Yeah.
the other type of function.
3D.1. There are a lot of them right now. 12.
Yeah, it's question 13.
Cool. All right. I think what's intimidating about this one perhaps is that
There's no numbers, maybe?
there's no numbers in there, and it's looking like alphabet soup because there's a lot of letters.
Yeah.
All right, but I think it's one of those things you just have to trust that it's doable because they've asked you to do it. When they say a local maximum happens when f dash t is equal to 0. And same with the local minimum. So we're really looking for where the first derivative is equal to 0, because that's when the slope is horizontal at a point, so it must be turning.
Yeah.
And point 2 is looking at where the second derivative of ft is equal to 0.
Yeah.
So the point of inflection is where we're going from concave up to concave down, and that happens where second derivative is equal to 0. So let's derive it. Ft equals AT.
Are we going to use the product rule for this?
We are, yeah. So I'll just go straight into product rule. I would let the first one be AT, and therefore U dash is just A. And I would let the next one be e to the minus bt, and therefore v dash is minus b e to the minus bt. And yeah, glorious, we had no numbers at all. Are you happy about v dash, where that minus b come from? Cool.
Yeah.
So f dash t is equal to u dash v a e to the minus bt.
Mr. Bundenberg, I have
Yeah.
a quick question.
Yeah.
So at today lunchtime, like do we have math help in the TLC?
Ooh. Yeah, I expect Mr. Crawley will be there. Yeah.
Okay, thank you. That's all. And did I rickroll to everyone?
The sound didn't work. Sorry.
Oh no.
You forgot to click the box saying share sound.
Okay, so I actually rickrolled. All right. Okay.
Will there
Thank
be a
you.
Zoom
Bye.
math up?
Well, I could just stay here. Does that work?
Sure.
I'll stay here until everyone's questions are answered. I've got a double free after lunch, so we can just put in a long Zoom. Where was I up to? U dash v dash u.
Yeah.
So that would be then minus at e to the minus bt.
Would it be negative BE?
Yeah, I put the
Oh.
I snuck the negative. Oh wait, I've missed a b, haven't I?
You missed, yeah.
B e to the minus b.
Yeah.
Thank you.
Okay.
And then for simplicity's sake, we can write that plus minus as just a minus.
Yeah.
All right. And then because we want to solve for the turning point, we're going to set it equal to 0. So 0 equals that whole thing. I'm going to now factorize everything that's common. So both things have an a e to the minus bt bracket. So yeah, a really good solution, especially for these exponential type problems, is if you can take a common factor out.
Yeah.
If I factor out ae to the minus bt, what needs to go here in place of the first term? Like in place of that? Yeah, nice, 1. And what needs to go in the place of, pardon?
Would the next one just be TB?
Yeah, it would be. Why is there a T there?
Because the U is equal to AT with V dash U in the second part of the
Oh, yeah.
product.
Yep, we're all good. All right, now we want this to equal 0. So really there are two halves to it. There is the left-hand half. Let's talk about the left-hand half. A is a constant and it's positive, so it's not going to give us a 0. E to the power of anything is also going to be always positive. So you're not going to get a solution from this side. It's just not going to work. However, you could get a solution from the other side. 1 minus TB could actually equal 0.
Yeah.
So we're like, okay, let's take that to one side. That must equal 0. If I take 1 from both sides, minus TB equals -1. And then I divide by minus T. The minuses would cancel. And sorry, I'm not going to divide by minus T. I want T on its own. I'm going to divide by minus B. T will equal 1 on B.
Yep.
Which is what they asked us to find.
Oh, like
Yeah. I think it's even though it's just an alphabet jumble, once you factorize it, turns out a little more nicely.
yeah. Yeah, I think I was just probably intimidated by the fact that we had like learned a new chapter and then it was all letters and I was like, I don't want to do this.
Fair. All right, so yeah. Maximum, we found the T in terms of B for the maximum. Point of inflection. All right, point of inflection. The second derivative is equal to 0. There's sort of a long way and a short way to do this. Should we have a shot at the short way?
Yeah, sure.
Awesome. You see how that AT to the minus EBT differentiated to this
Yes.
after we did prior rule? Basically, when we want to find the second derivative, we're going to take this to one side and we are going to differentiate the first portion just regularly. So F double dash T will equal minus AB E to the minus BT. Are you happy that that red one differentiates to that?
And is that using the product rule?
Chain
Or
rule.
is that just like chain rule? Okay.
Yeah, because that minus B is coming out the front.
Yeah.
Cool.
Let me just process that like really quickly. Yeah.
Yeah. Because yeah, the derivative of minus BT is just minus B, so it comes out the front. And then this portion here, I'm underlining in grey,
Yep.
is actually the same as the original function. AT to the minus EBT. Oh, no, it's not, is it? There's a B in there. Ignore me. There's no shortcut way to do this. This bit here, we're going to have to use using product rule. So my U will be minus AT B. And my V is going to be E to the minus BT.
Yeah.
All right, and then differentiating U dash is just going to be minus AB.
Yeah.
And V dash will be minus B E to the minus BT.
Yeah.
All right, and then we put that on to the back of this one we've already got here. So we add on U dash V. So that's minus A B E to the minus BT plus v dash u minus a t b multiplied by minus b e to the minus b t. Oh, it's a bit of a mess, but we'll tidy it up in terms of negatives. F double dash t is minus a b e to the minus bt minus a b e to the minus bt.
Yep.
Now there's two negatives happening there, so then it's plus a t, right, actually it's a b squared t e to the minus b t.
Yeah.
It is. Bless you. All right, so you see these ones here?
Yeah.
They're the same. So what we can do is we can basically collect them like terms. And instead of minus one lot of it and minus one lot of it, I can just write minus 2 AB e to the minus BT. And that's both of those combining into that.
Yeah.
Right. Then what we're going to do is take out every common factor we can and set it equal to 0. So I think we can take out an A and a B from both and an e to the minus BT from both.
Yeah.
And then what remains is a minus 2
Yeah.
plus,
T.
I think
Oh.
BT. There's another B left there, isn't there?
Yeah.
All right. Now, same sort of logic as before. This left-hand term will never equal 0 for us. So the right-hand term will be the one giving us our solutions. So we can say that minus 2 plus BT equals 0.
Yeah.
Add 2 to both sides. So BT equals 2. And then to get T by itself, T is equal to 2 on B.
Yay. Okay. Amazing. That's satisfying once you actually get the answer.
It is when it actually comes out, yeah.
Yeah.
All right, sketch the function showing the features you've shown. Oh,
Would we be able to use our calculator?
yeah.
Because if I'm going to have my calculator and it wants me to do it by myself, I'm definitely still going to use my calculator.
Fair. I would just make up a value for A and make up a value for B and then do a calculator. You can get that nice logistics search function code.
So would I put any constants in, like,
Yeah.
and I would just say that I would be like, assume A is this and assume B is that. And
Yeah,
then-
and you'll get a curve that looks like that.
Yeah.
Oh,
I sure hope not.
no, that's my pen doing something strange. My hands are not shaking that bad. Okay, yeah. But you'll get one of those curves.
All right. I'll try and do 14 on my own now.
All right,
So
yeah,
I think
14 again looks like alphabet soup.
Yeah.
But use quotient rule and it will, yeah.
Okay. Awesome.
Okay,
Thank you so much for your help. That's really
pleasure. Anytime.
good. Yeah, and I'll email you if I have any problems.
Lila or Ewan, do you guys have questions?
Yeah, I do have questions.
Awesome.
Sorry, I'll just have a quick look and
Yeah.
tell you which one.
I have a question.
Yes,
After
Ewan.
Lila. 3D.1 question 10 is the one question that I can't do, and then I can finally cross it off my list. See, look, it's really disturbing me how no, this is my week, and I can't cross off 3D.1 question 10, the little bottom corner there. It's annoying me, I'm not gonna lie.
Is that this one?
Yeah,
All right.
I found A and I found B,
Mhm.
and then I got to C, and it kind of pooped me out because I kept finding the derivative as f dash x is equal to x on x squared. So either way, you have a 0 error.
Very weird. Let me try and find the derivative, shall I? All right.
But maybe I'm just stupid. And on question 13 as well, what did you find f dash x to be? Like the one that you just did.
F dash x was there highlighted in yellow, circled in yellow.
Okay.
So a e to the minus bt minus a t b e to the minus bt.
Cool.
And then you factor out a e to the minus bt.
Yeah, no, I got the same answer. I just wanted to double check that my derivative was correct.
Cool. And then the factored version gives you a thing in brackets here that gets you your answer.
Nice.
All right. U equals e to the x, v equals x, u dash equals e to the x, v dash equals 1. All right, so then u dash v take v dash u over v squared is equal to e to the x dot x take e to the x dot 1 over x squared, which is e to the x bracket x take 1 over x squared. Is that what you got?
Mm-hmm.
But that's good, isn't it?
No.
So then this, if you're looking for a stationary point, you set it equal to 0.
Yeah.
And
then
the
you have
only
the-
time that will equal 0 is when x equals 1.
No, but then you have the issue with it equaling 0, like the bottom bit.
But you can put 1 on the bottom.
No, but like, oh,
Like
no, I keep going wrong, man.
x can't equal 0, but you can have x equal to 1. That's no worries.
Yeah. That's really stupid of me.
I mean, no, it's not, but I can't see what you did. What happened?
Oh, I had the same derivative and it just trumped me. I just kept going in circles and I couldn't find it. I just have a bunch of question marks on my page. Oh no, that's for the second derivative. Sorry. No, I got the same. No, that was for the second derivative.
All right.
For finding this stationary point of inflection, I think, or something like that.
Yeah, so now it asks for, well, find and classify all stationary points. Well, we found them. We haven't classified them yet, but I'm sure you can classify it, yeah?
Yeah.
It's a sign diagram. It's either going to be positive or negative. Find the interval. Okay, so now we want to find the second derivative. Yeah?
Yep.
All right, so second derivative.
And it's only turning, no, it's only stationary points of inflection you find the second derivative for.
No.
No? Everything is done first derivative.
Sorry, you mean it's only like where it goes, it's only inflection points you do second derivative for.
Okay.
Yeah, so and inflection points are going to give us the concave up and concave down.
Yeah.
Anyway, so I would probably take it from here and say that u is, oh, maybe take it from there then. U is e to the x, x take 1, and v is x squared. Therefore, u dash is, oh, it's so mean.
X. It's just e to the x, x take 1.
No, it's not.
Yeah, it wouldn't it be? That's what I did.
No, it's product rule. You have to use product rule within product rule.
I did chain rule. That's probably why my answer's poopy.
Yeah, no, you'll have to
No,
use.
I got my
product.
second derivative to be equal to x ex take ex take 2x x ex take ex to the negative x on x on x to the power of 4.
Well, it's certainly on x to the power of 4. I don't know about the rest of it.
Which
Let me-
sounds like
Let me just figure it out. U dash x plus. Oh, it's just gonna be that. That's okay. All right, then it is what u dash v take v dash.
why
U-
wouldn't it be x to the power of 4?
Because you're doing x squared, v squared, which is x squared squared. So it'll go to the power of 4 that way.
Yeah, that's what I said.
Yeah, that's good. All
You
right,
said
u
it wasn't.
dash.
Sorry, I got confused.
Oh no, sorry. E to the x bracket x take 1 bracket plus e to the x. Lots of v. Minus v dash e to the x take 1 over x to the power of 4. All right, I suppose there's some tidying to be done on the top.
Which is, yeah, so I had that as well.
If I was going to tidy the top, I would take an x out the front and e to the x. So x e to the x. That would leave me with x minus 1 plus 1
Mm-hmm.
minus 2 x minus 1 over x to the 4 equals x e to the x. X minus 1 plus 1 is just x. Minus 2x. X minus 2x is minus x plus 2 over x to the 4. That then gives me a couple of zeros. One is at 0, but that doesn't work because you can't divide by 0. The other is at x equals to 2.
Yep.
And then we draw a sign diagram for 2x f dash x.
F double dash.
Double dash x, yeah.
Okay.
All right. Then we choose
From there, I know how to go. Is there
Yeah.
any like easier way of finding x like that, or is that it literally you have to like algebraically? There's no calculator cut. Check your answer unless you graph the function.
Even graphing the function, your calculator can't pick inflection points. But if you graph the first derivative and pick the maximum or the minimum, whichever it is, that will give you the that will give you x. That should occur at x equals 2.
Okay. Right. Thank you. Yeah, that's really all the questions I had. I had another question. I think a thing that's really held me back this topic is one, the sign questions within 3D.1, which there is none. And like pulling things out of the bracket, like to like simplify them. Like when you pulled that all out to tidy up, like x e to the x, like I just can't see how you pulled that out for the whole equation. And like expanding it makes sense and I understand. I just can't look at it and go, this is what I need to pull out. Do you have like any worksheets for like natural logs and e to the power of x, like pulling stuff out, just practice other than that's not in the questions?
That's not the question. Worked examples for like factoring out e to the x.
Yeah.
Yeah, I will have a hunt. And you wanted for trig as well.
Yeah, because it just doesn't. Yeah, I need practice.
Yeah. So
If you don't
Fact-
have
the fact-
anything,
I certainly have trig practice for solving trig equations.
It's just practicing like pulling out like X. So like year 9 maths.
Yeah, but you want to be doing it with e to the x, don't you?
Yeah, with not like year 9 pulling it out, but like the same like worksheet, but with e to the x and natural logs and stuff.
Yeah.
I don't know if you have anything. I was just wondering, just worth the shot to ask.
Certainly worth the shot to ask. I have trig practice. I don't have any of that type of factoring practice. Yeah, you're right. It is a
Okay.
skill to be able to spot it.
Because otherwise, I don't think like if I got that, like I got to where you got there, like x e to the x, I don't think I could have gone further if it was in a sat. Like it would be a struggle.
All right. Well,
Like looking at it, I understand how you've done it, but I just couldn't do it. Like I couldn't replicate it without seeing someone do it.
yeah, fair. There's probably a long way to go about it. Here, so if you did get here,
Because if I was in that boat right now, what
you'd
I would do
expand
is
and
I would
simplify.
I'd factorize out the -2, so -2x plus 2. And then I would factor in the x e to the x to the x take 1, and then go from there.
Yeah.
Like that's what my brain's telling me to do.
Another way to do it is just to expand everything in, which is ugly, collect like terms, and then factorize, and you'd end up at the same point.
Yeah, I just can't factorize.
Yeah.
Oh, well, I'll figure it out.
I'll ask Mr. Crawley and Dr. Zhao if they have any that sort of factor practice happening. But
Thank you.
yeah, no worries.
That's fixed my question. It's just yeah, it just would be good to get some more practice. But thanks for your help.
Later. Either.
So yeah, have a good lunch.
Thank you. Lala, did you have the questions?
Yeah, I do. So the first one is 3D.1, question 3D. I've gotten stuck at the end and I just can't figure out what I've done. Well, I don't even know if it's right, but I'm just confused, I think.
Fair. Is that this one? D?
Yeah, that one there.
All right. So we're looking for inflection points, so we want second derivative, right? So F. Well,
You only find inflection points with the second derivative.
pardon?
Are you saying that you only find inflection points with the second derivative?
Yeah, because inflection is when it goes from concave up to concave down, or vice versa.
Mm-hmm.
So, and that will need to be a second derivative.
Okay.
So first derivative is going to be what? Minus 12x to the power of 3 minus 24x squared. And then second derivative is minus 36x squared minus 48x.
Mhm.
From here, you set that equal to 0. And then any ideas how to sort of go about solving?
You take out the -6x.
Nice. I'd probably go further and take out -12x. But yeah, negative
Oh,
6
yeah,
would be,
I didn't
negative
even-
6 would be fine.
Yeah.
And that will leave you with 3x plus 4.
Mm-hmm.
Then you've got two solutions. Your solutions come from either x equals 0,
Mm-hmm.
or you set 3x plus 4 to equal 0, and then like take 4 from both sides and divide by 3,
Mm-hmm.
and x equals minus 4 on 3.
Yeah.
Then our sign diagram for the second derivative, f double dash x, is occurring at 0, -4 on 3 and 0. It means there are going to be points of inflection at those two, but we don't know what type of points of inflection they are, like whether they are going concave up to concave down or vice versa.
Yeah.
So we basically sub in values at this point. I would sub in, -2 into here. If you sub -2 into there, you're going to get a positive number because -12 times -2 is positive, and then 3 lots of -2 plus 4 is negative. So it'll be a negative overall.
So you're putting it back into the second derivative?
Yeah, into the second derivative.
Okay.
If you want to find the location of them, like the y coordinate of the inflection point, you put it back into the original. But for just checking the signs, you put it back into the derivative because you want, so you want to know, for example, this is concave down.
Yeah.
So concave down, and then in here, you put in, I don't know, -1. -1 in there is going to come out to be, what is it going to be? -1, it's positive. Times a positive is positive. And then if you put in the +1, the first number is going to be negative, so the whole thing will be, negative. Your graph is going concave down, concave up, concave down. And your two inflection points are at x equals 0 and -4 on 3. And I guess we want to double check whether they're going to be stationary points of inflection or non-stationary points.
Yeah.
Do you know the difference between stationary or non-stationary?
I was just trying to find it in my book now.
Yeah.
Isn't it when the sign diagram like looks? So that would be a non-stationary inflection point. The -4/3.
You're right, that will be non-stationary. Yeah.
Mhm.
The other one though will be, I think, will be stationary. Yeah, I'll graph the original function because often you can see it from the original one.
Okay.
All right, if you look there, I know it's kind of hard to see, but you see how here it's completely concave down. And then at some point, maybe here where my arrow is, it starts going concave up.
Yeah.
And that's the -4 on 3 point. And we can see because it's so sloped there, that is a non-stationary inflection point. Here though, you see how it appears to flatten off when it goes from concave up to concave down again?
Yeah.
That flat point there will be a stationary inflection point.
Okay.
So it is a stationary inflection point if f dash x equals 0 as well. So if the first derivative is 0, it means that it is flat, and it's therefore stay in it, and so it's flat and going concave up to concave down. So it's what's happening is that graph there. So a good thing to do to check is to take these values and put them into the first derivative as well. If you put them into the first derivative, the -4 on 3 will give you a negative number, meaning the slope at -4 on 3 is negative, so it's a non-stationary inflection point.
Okay.
But if you put in 0, it will
It's
give
gonna
you
be-
a slope of 0, which tells you it's a stationary inflection point.
Right. Okay. Yeah. That makes sense.
Cool. Yeah. That's found and classified, I guess.
Okay, that's good. I will hopefully remember that. Sorry, I'm just trying to find where I got up to. Oh, with 3G, question 3C, I got all the way up to like writing the doing the derivative and then making it equal to 0, but then I didn't know how to find what x was from there.
All right. So 3C. Cool. What was your derivative? Just to save me doing it.
Where is it? I got negative 8,000 over x squared plus 2x.
Negative 8,000 over x squared plus 2x. Weird.
I don't know if that's
For the first derivative.
the
Oh,
2x
right.
is separate. Like,
Oh,
yeah.
I was like, no. Yeah, okay, nice. And we want that to equal 0, don't we?
Mhm.
All right, so let's set it equal to 0. All right, I would at this stage multiply everything by x squared.
Mhm.
That's because we don't really like fractions. If you multiply the 0 by x squared, it stays 0. Then you get minus 8,000 plus 2x cubed.
Mhm.
And I would then add 8,000 to both sides.
Yeah.
8,000 equals 2x cubed. And then I would divide both sides by 2.
Yeah.
4,000 equals x cubed, and then cube root both sides.
So can you just leave it written like that?
Yeah. And whatever it is, centimeters or whatever. So that would be the exact answer. It
Mhm.
might be that the answer in the back of the book is the decimal approximation. So it is the cube root of 4, whatever the cube root of 4,000 is. Right, grab my calculator.
Oh, maybe, yeah. I'll see what the answer is. 3G question. What question is this? 3.
3. Is it 15.87?
Yeah, it is.
Cool.
Oh, so then they wait, but then in the answers they have that written as that times that again times 7.94. Is that where's the question going?
The question says find the minimum dimensions of the box.
Yeah.
So you see how a box can have dimensions of like base, height, base length, and height.
Mhm.
So the dimensions are 15.87 by 15.87, and then you need to find the y. But if you look in part A of the equation, y is equal to 2,000 on x squared.
Oh,
So
right.
put in the x squared value there,
Mm-hmm. Oh,
and that will give you the y.
that makes sense. So then for D, would I
Yeah.
put in what would I do for D then?
So you see up above in B, you found a formula for the surface area.
Mm-hmm.
Basically, to find the minimum surface area, you put in that value of x, which we found that gives us a minimum. So you put in the x value into that formula in B, and it will give us the total surface area.
Okay, that makes sense. Sorry, I feel bad. I keep asking you so many questions.
No, that's good. That's exactly what I'm here for.
That's fine. What else is there? In 2B, I found the derivative using of 3G as well for 2B. I found the derivative using the quotient, using the product rule. But then I got the wrong answer somewhere down the track because I don't know what I did wrong, but
2B. So what was the formula you used?
what the formula?
Mm.
Oh, I used 4x, the area formula, and found the derivative of that using the product rule. So 4x.
Hang on. I'll just put it on the screen.
Mhm.
Screen share. All right. Find the area in terms of x only. So you were saying the area is what, 4x?
Oh no, the area is 4x times by the square root of 25 take x squared.
Yeah, it was. Cool. All right, and then you did product rule, which is right. So u is 4x, u dash is 4, v is 25 take x squared to the power of a half, v dash is a half 25 take x squared to the minus a half multiplied by 2x, which could also be written as,
Wait, isn't it negative 2x?
yep, minus 2x. And then this 2 and that half are kind of going to cancel, and you'll just be left with minus x over the square root of 25 take x squared.
Yeah.
All right, and then so u dash v is 4 root 25 take x squared plus v dash u. That's going to be 4 minus 4x squared over root 25 take x squared. And you wanted to find the minimum of this to set it equal to 0? All right. I would multiply everything by root 25 take x squared. You see how my normal attack on these problems is just get rid of the denominator.
Yeah.
If you get rid of the denominator, what's really neat is that this turns into 4 brackets 25 take x squared. You no longer need that root because the root and the root cancel. Then you're just left with minus 4x squared equals 0. From there, 4 times 25 is 100. Take 4x squared, take another 4x squared equals 0.
That's right. Oh, maybe I did it. I think I got up to there, but instead of getting minus 4x squared, I got plus 4x squared.
Oh,
And so
okay,
then
and
I
then
was
they
like-
cancelled out.
Yeah, and then I was
Yeah.
like, what?
Yeah. So then I'd say 100 equals 8x squared. X equals the square root of 100 on 8.
Yeah.
Which is 10 on 2 root 2, or a decimal. Yeah, because you're square rooting the top and the bottom.
Yeah. Okay, yeah, that makes sense. Yeah, I can definitely do that now. I think I only had one more thing.
Cool.
Where is it? Oh, I asked you that one. It's from a bit further back. Sorry. No, I've done that. That's fine. Maybe that is it, actually.
Keeps going, yeah.
Oh, I was just wondering if you could help me with in question 3D.1, number 1, with how to describe the turning points of y equals f of x. I just didn't really understand what that meant. by
When
describe?
So when it says describe the turning point, it should either be a maximum or a minimum.
Oh, so that's all you say is that.
Yeah. Hang on, let me get to 3D.1.
Mhm.
Oh, B, C. Yeah. So it'll be either a maximum or a minimum.
Oh, okay, right. That's not that bad then.
Yeah, so turning points are either maximum or minimums, and inflection points are either stationary or non-stationary.
Oh, okay, cool. That's pretty straightforward. Okay, I think that's it then actually.
Yeah, awesome.
I'll let you know on Monday when I finally come back to school if I have any more questions.
I'm looking forward to having you guys back.
Yeah, I think it should be good.
Cool, cool. Do send me an email if you get stuck tomorrow or anything.
I will. Thank you for all your help.
My pleasure. See
Thank
ya.
you. Bye.